Okay, we're back with part 2 of this lecture on arithmetic sequences. If you remember last time we looked at a task where we had arranging some seats for a band in semicircles, and we were going to count that, how many seats were in each row. And we have a similar thing we're going to do now that's arranging blocks. Now once again, you should have actually already have done this particular task as part of the several tasks that you were asked to do before you started these videos. So if you haven't done those tasks, be sure that you do them. But after you've done that, come along and let's take a look at this particular video here. So we're going to do a similar task to one that you were asked to do earlier. Suppose we start with a collection of 8 blocks, and at each step of the process we add an additional 4 blocks to the collection. We want to determine the number of blocks in the collection after X steps, and so after 0 steps we still have the initial collection of 8 blocks. Actually, I want to change that. I want to make that start with 7 blocks and add 4 each time. Okay, so what we want to do is we want to start with 7 blocks, add 4 each time. So after 0 steps we still have our original 7 blocks, and the next step we'll have 4 more than that, and after 2 steps we'll have 4 more than we did before. So we want to draw out a physical representation of the layout of the blocks, it should say, and write down a recursive formula for y, the number of blocks, as a function of x, which step we've completed. And so we'll make a table of values where the input is x as a step number and output y is the number of blocks in the collection. Then we'll write down an explicit non-recursive formula for y as a function of x, and then we'll get a Cartesian graph of the relation on graph paper. So let's take a look at this. So here we are, we start with 7 blocks, and each step of the process we add additional 4 blocks. And so after 0 steps we have our initial collection of 7 blocks, and the order pairs you see here are step completed, number of blocks. So 0 steps, we've got 7 blocks. 1 step we add 4 to that for 11 blocks. So this is one way we could arrange the blocks, not the only way of course. And we can see then 2 steps. After we complete that we have 15 blocks and so forth, and you can see the arrangements there. And so the sequence of outputs, which is sometimes how you'll see a sequence written, you'll just ignore the inputs. So in this particular case the 7 goes with an input of 0, so the first one is actually the 0th step, or after 0 steps, an input of 0, and then input of 1, 2, 3, 4, 5, and so forth. So since that part is sort of automatic, we don't have to write that part down. Now I have this actually in a Sketchpad sketch, so let's go back to our Sketchpad sketch. This is the same one that has the set up there with the seating arrangements. And this one we have y0 is our number of blocks that we start with, which is 7, and m is the amount we're going to add each time, which is 4. And x is which step number we're on. So right now we're on step 0, and if I just click on that and press plus, it's going to go up. So I click on the equals and go up. I can actually type in a number 2 if I want to here, but I can also go on this and press plus. And notice each time we're adding 4 blocks to the previous arrangement, and the y value there is the total number of blocks. Now what does a table look like? Well, here's a table, at least the first part of a table, and so right now we're at the 0th step where we have step 0 and 7 blocks. If we hit plus here, we move down to the 111 ordered pair, and you can see the 11 blocks down here. 215, you can see the blocks, and so you can see the arrow is pointing to the part of the table that's represented by the drawing over here and the y value over here in red, and the x value that's there that's generating it. So we can see the table. So recursively, what are we doing in the table? We're taking the previous value and adding 4. So we start with 7, then the next value is 7 plus 4 to get 11. The next one's 11 plus 4, and so forth. So how do we get a recursive formula? Notice that basically what you're looking at here in the table, if we want to find a particular x value, like 12 here is x, then we go to the one before it, so we subtract 1 from x, that would put us at 11. Find its y value, f of 11, which is 51, and then add 4 to get 55. And so we're just taking f of x minus 1 plus m to get f of x. and this works for all of the natural number x's. And then we have to also know that f of 0 is 7. So we have our initial step, and then it tells us how to get to the next step. Here I'm using actual regular function notation, whereas before I used more sequence notation. So sequence notation uses subscripts. Normal function notation uses the parentheses. And whether I call it f or y, that's the output. Okay, well, as we saw in the other example, another way to think of this is start with the 7, and then we're adding 4. And then we take that 7 plus 4 and add another 4. And that 7 plus 4 plus 4 and add another 4. And so forth. And we're just continually, well, each step we're just adding a different, or adding an additional 4. So we have a different number of 4s here added. So what we basically have here is just 7 plus a bunch of 4s each time. Okay, so once you see it that way, then it's not too hard to find the explicit formula. Repeated addition can be written as multiplication. So here we have, for example, at this step here, we have, let's say this one here, we have 3 4s, so it's 3 times 4 plus a 7, or 7 plus 3 times 4, I rewrote it this order, 4 times 3 plus 7. Now if you look, even the first one can be thought of as 4 times 0 plus 7. So they can all be thought of as 4 times some number plus 7. The number I have here in the parentheses is the same as the x number this time, since we started with the 0th amount. And so the number in parentheses is actually the step number. The 7 is our initial value, and the 4 is what we call the slope, or delta y, or the common difference. It's what we're adding each time to y to get the next y if we increase 1 in x. So if delta x is 1, delta y is 4, and that is the slope, which we call m. So since this is just, if we put an arbitrary x in here, then this number in parentheses becomes just x. So our explicit formula then is just y equals 4x plus 7. Now, notice that this is dynamic, so I can put another number in here. Suppose I wanted to start with 16. That just starts with more blocks, and say if I wanted to go up by, instead of by 4s, suppose I want to go up by 3. Notice everything is adjusted dynamically, and we get the formula 3x plus 16. It even works if I go down for the slope. Well, some of it works. Let's say if I start at 16 and work our way down, this blocks thing doesn't work anymore, but the rest of the sketch does work correctly. I'm repeatedly adding a negative 2, so even when you have a negative number there, it works. Even if you start with a decimal, let's say 2.5, and let's say we want to add 4 each time. Let's see, let's go back here. This is going up, but it's these are rounded off. These are rounded off in whole numbers, so let me, I can fix that. Let's see here. So maybe tell it to round off in tenths, and now we get that. And now this one's not rounded off in tenths, so I need to do the same there. Rather than fix that right now, I'm going to go ahead and just go back. But it would work the same if you go up by fractions. If it's a sequence, notice that the input has to be a natural number or perhaps a whole number, but the outputs can be anything. They don't even have to be real numbers. They can be complex numbers, they can be rational, real numbers, integers, whatever. They can be anything. Now in this case, when we're talking about a number of blocks, for the drawing to work, we need to start with a positive number of blocks and then go up. It still makes sense in blocks to talk about going down by 2, Although what happens here, once you reach 0 blocks, then it really doesn't make any sense anymore in terms of a blocks model. But there are other things, other types of sequences where it would make sense. So let's go back to our original one. Let's see, it was start with 7, wasn't it? And then go up by 4, I believe. And so this is what we have here. I can, now that I have an explicit formula here, for example, I could put in 100. Say 4 times 100 is 400 plus 7 is 407. And this does know how to do that, so I can type in 400. And it does, not 400, I meant to say 100. And so we get 407 for the output. So I can go directly to a particular one. Now let me show you something else here. If we had just started with the first step of 11 and we didn't have a 0 step, we might have written this formula as 4 times x minus 1 plus 11. That's the way we did the one when we did the seating example. But notice we're using the point 1, 11 in the slope of 4. So that's a point slope formula. Well, there's not just one point slope formula. There's a point slope formula for every point. So we can center this up, for example, at 215. We just have to make this x minus 2 times 4, and then plus 15. So notice that the 4 here is the slope. That doesn't change. Now if I change the slope, those will all be different. But it's just this number here is this slope here. It's how much you're adding each time here. And notice that this will work out correctly. So let's check out one of these in the middle here. Let's say 6. So if we plug in 6, 6 minus 6 is 0 times 4 is 0 plus 31 is 31. So if you have x minus whatever the x is here, notice when you plug in that x, this part's all going to go to 0, and so this number here needs to be the output that goes with that input. Okay? Now, the slope being 4, put the 4 there, and everything works out right. Let's check it out, some numbers here. Put it in this formula. Plug in 7. 7 minus 6 is 1 times 4 is 4 plus 34 is 35. Let's check out another one, 11. 11 minus 6 is 5 times 4 is 20 plus 31 is 51. So that checks out. Even sum back here, 0. 0 minus 6 is negative 6 times 4 is negative 24 plus 31 is 7. So this does work out if you do this. So now we have a slope, a point slope formula, and the point is x1 comma y1, and the slope is m, and so the output y equals m times parentheses x minus input, the specific input x1 plus the y output y1. Okay, so we have a point slope formula for every single point. And all of these are really the same formula. All of these things are exactly the same formula. They just, it's manipulated in a different way. So if I were to use the distributive property here and combine like terms, I would be back at 4x plus 7. So for example, if I'm down here, 4 times x is 4x. 4 times negative 10 is negative 40. Negative 40 plus 47 is back to the 7. So there you can see that those are really the same formula. Now if I graph this, we get dots here, and you notice that every time you go to the right one, you go up whatever m is, in this case 4. Notice this one does have a point on the y-axis, 0, 7, so that y sub 0 is the initial y, which is a y coordinate of the y-intercept. So there we go right there. Right one up 4, right one up 4, right one up 4, right one up 4. And that makes this straight, and so we see that that is a straight line. So if we were to connect the dots, we would get a straight line. Now in this particular case, it doesn't make sense to connect the dots because we're talking about blocks. So this is truly an arithmetic sequence rather than a continuous linear function. But in our next section, we're going to talk about extending the domain so that we talk about functions of this type whose domain is all reals. And for certain types of data, that makes sense. So let's go back to here and just look at what we have on our PowerPoint so you can see these different sequence of block arrangements. And let's go ahead and just go back to here. So this is the table. There's your recursive formula worked out, the steps leading to a non-recursive formula there, and then the point slope forms, and then there's the graph. So let's review real fast. And arithmetic sequences, if we summarize, notice that they're basically linear functions with the domain restricted to the natural numbers or perhaps the whole numbers. They are one-to-one functions. The domain, either it's going to be the first n natural numbers, the first n whole numbers, or all natural numbers or all whole numbers. Those are sort of the options there. Recursive definition, you always have an initial term, and so you start by specifying the initial term, a sub 0 equals some particular number, or perhaps a sub 1 equals some particular number. And then you have a recurrence relation that adds a specific constant number m to the previous term, to the output, to obtain the next term, a sub k equals a sub k minus 1 plus that number m. In fact, you can really define these with any term, as we kind of saw from the point slope form. As long as you have that recurrence relation in any one term, you can kind of figure out the rest. So the slope, m, is the common difference between successive terms. It's the change in the output when the input is increased by 1. It's the constant amount that's added to the output each time when going up one step. So the slope is delta a if a is your output, and if k is the input, when delta k equals 1. Or if we use the x and y, the slope is delta y when delta x equals 1. So for a non-recursive formula, in the slope-intercept, y-intercept form, a sub k equals mk plus a sub 0. That is 0, comma, that should say a sub 0 is the y-intercept if it's actually present. If it's not, it's what would be if you extend the pattern to have a y-intercept. So if you start at k equals 1, then of course a sub 0 is just a1 minus m, even though that's not really part of the sequence if the sequence starts at 1, but m is the slope, called the slope. If you want a non-recursive formula in point slope form, there are infinitely many of those, one for each input. You have a sub k equals m times k minus k1 plus a1, where k1, a1 is any particular point in the sequence and m is the slope. Or if we use our x's and y's, we would say y equals m times x minus x1 plus y1, where x1, y1 is a point, and again m is a slope. In a dynagraph, which we didn't look at in this video, but we did in the last video, inputs are evenly spaced, one apart, and outputs are also evenly spaced, but m apart. And so the arrows are actually going to be parallel in those every time we go over m to get the new output. So a regular graph or Cartesian graph, we have a collinear set of dots, so the dots are all in a straight line. And we get one for each domain value, and they're spaced 1 unit apart horizontally, but m units apart vertically. So you go to the right one, you go up m units. Of course, if m is positive, you're going up. If m is negative, you're going down some by the absolute value of m. So we will pick up now in the next video on some applications and problem solving. We'll start with some where we look at different representations, and given one representation, find the others representations. Make sure we have a really good understanding of all of the structures involved in the table, the recursive formula, the non-recursive formula, the graph, dynagraphs, and so forth. And then we'll also then do some problem solving, put this in the context of real-world problems.